Welcome everybody in the lecture hall. Welcome everybody on Zoom. Welcome everybody watching us from the future. Today I'm teaching on Wi-Fi because the cable seems to be on strike today. We'll see if we can fix it. So it might be if at some point the people on Zoom start seeing pixels, I call pixelated or bad quality, then that would be just because of it. So if it ever happens, then you can help in the lecture hall by trying to disconnect from the Wi-Fi. But as long as it works, then it's working. And the USB Verlängerungskabel is sponsored by FIS. So it's thanks to them that I'm able to actually broadcast these sounds on Zoom. So I'm going to start with a question to check that you've been following what I told you last week. So what is the best practice? Do you first try to scale out, then try, if it doesn't work, try to make the code better, and then scale up? Or do you first try to make the code better, then you scale out, then you scale up? Or do you first try to scale up, then scale out, then make the code better? Or the other doesn't play any role, one should just try everything? Wow, 91%. Still answers coming in. Wonderful. Okay, so the majority is in fact correct. Indeed, that's what I told you. The first thing you should do is try to make the code better. How do you do it? You just do it on your laptop. So what you typically do is you take 1/10 of the data set or 1/100th of the data set, like a small size, then you improve the code on your laptop. And when it works and it's faster, then you can either maybe make it work all on your laptop because suddenly it fits, or you can then upgrade the code that runs on the cluster, and then you're going to get something faster. Then, of course, if it doesn't fit on your laptop, you scale out. Scaling out means you go to multiple machines, cheap machines, but a lot of them. Scale out, scale in would be reducing the number of machines. Scaling up means you have more memory, more CPU, so more expensive machines. But this is really the last thing that you should actually try. In fact, these days, scaling out and scaling in is handled automatically by many cloud providers. For example, Amazon, Azure, they can all automatically adapt the number of machines that are running dynamically depending on the number of people who are on your website. Yes, we have a question over here. We maybe use the over here.
I don't quite see why you would scale out first before scaling up. So let's say I have a shitty laptop from 2015 and it doesn't work. So I think the smart thing is to upgrade the laptop, because if I scale out, I'll have all the, all the inefficiencies of parallelism and all that stuff. And there are papers which say, you don't need Hadoop, you can just do your Unix stuff.
Yes, so you're absolutely correct. So this is a guiding principle, right? It's a general guiding principle. But of course, in practice, at ETH, we teach you to think critically. And of course, there are cases in which it makes sense to scale up. For example, you can upgrade to a newer laptop that's scaling up. In that case, it makes total sense, right? Then you know what you are doing. If you already have a standard configuration, imagine that you're just missing a tiny little bit, then you can either upgrade to a new laptop or go to a data center. Then you have to think about the cost. The cost of purchasing a new laptop, if you're just barely, you just need a tiny bit more, that might be more expensive than just renting some machines for an hour on Amazon, that kind of thing. So you really need to adapt to every situation if it makes sense. But the message that I want to give you here is to always try to start with the code. Try to see if you can store the data more efficiently, if you can write more efficient code, because in many, many cases, you're going to manage to make it run on a single machine. So this is the first guiding principle, and this is true for many people who start with a project. And the second principle is that when you are in the cloud, at the asymptotic limit, scaling out makes more sense economically. The reason is that when you scale out, it's linear. So unless you have supply issues on the market of hardware, basically it's linear. One more machine is the cost of one machine. 100 new machines is the cost, is 100 times this cost. But scaling with the same factor on a computer, like 10 times as much working memory or 10 times as many CPUs, that's not going to be just 10 times the cost. That's going to be much more than that, because if you have 32 gigabytes of RAM, then getting a computer with 320 gigabytes of RAM is going to be much more expensive than just 10 times the price. Right, so this is basically the idea. But of course, you have to adapt it to every situation. Right? There are situations in which you might consider that it's worth it to purchase a newer laptop because you have an old one. Right? Does it make sense? Yeah. All right. But it's very good to think critically, right? You should.
There's
always.
also a question on Zoom.
There's another one.
Follow up.
Yeah.
But buying a new machine, a new laptop, isn't considered scaling out and not up. I think there's a.
If you continue to use the former laptop in addition to your new one, then that's scaling out. But then you have to consider the complexity of making the two of them work together, because it's going to be much easier to just trigger 2 or 3 machines on Amazon with a few clicks than configuring HDFS on these 2 laptops with heterogeneous configurations. So again, it depends on every situation, right? But technically, yes, if you add one more laptop, it's scaling out. If you replace the laptop with another one, then that's scaling up, right? Did that answer your question? All right. So, I think that's the one. No, that's not the one. It should be the one. Yeah. But in general, it's very good to question everything, right? So first, because this is how you learn. And I might also not always be right. Maybe that sometimes I'm wrong. And this is also how new discoveries are made, right? It's people who basically try something else. And as it turns out, it actually works better. All right. So this is where we left. Last week, I was telling you about how we use virtual tokens in order to, it's basically about simulating that we have more machines. Imagine that you have 10 times as many tokens on the machine. You increase the number of points on that ring, right? And so the more points you have, the higher the likelihood that they are going to be more or less well distributed over it. And you can also consider that these tokens correspond to a similar workload in terms of keys, in such a way that the computers that have more memory and more CPU, they can be assigned more tokens. And the computers that have less memory and less CPU, they will have less tokens, right? So it gives you a bit of elasticity and flexibility. Obviously, I mean, here on the slides, I don't have enough space to draw so many points, but obviously you will try to not put the tokens for the same machine next to each other, right? So here you have 3 green tokens. In practice, you would try to spread them out in such a way that you don't store twice the same key values on the same machine, right? If you try to diversify the colors on the ring, then you're going to spread over more different machines. Okay, for whom is that clear? The tokens? All right, very good. So now it means that if a machine disappears, then these tokens become free and they are reassigned to other machines like this, and then the data is transferred. If it's a smooth, elegant crash, in the sense that the machine knows in advance it's going to leave and it politely warns the others, then it can transfer the key values. Otherwise, it's no big deal, because now you know that the key values are stored multiple times, not just on the next token, but on the 2, 3, 4 next tokens. So it means that this data is not lost for the 2 tokens that are orphans here. It's not lost. You just ask for the machine, for example, who is here, if they would have the data, and then you download it when you take over. All right. And if you add new machines, then you just redistribute the tokens, the responsibilities to the new machine. So you see, we still fulfill what we had before. Now, you remember that I told you about the CAP theorem, which is about choosing. There's the question. Yep, go ahead.
Thank you. I guess so earlier we discussed how like the way the with the keys are hashed, like I guess like I had the impression that like different devices or groups of devices were responsible for sort of contiguous ranges of the key hashes, but here like the tokens are sort of more dispersed or distributed like around the circle.
Yes, more than on my slide.
Oh,
in practice. Yeah.
oh, okay. So like in general, like it doesn't like matter how the tokens are like distributed, like with regards to like each machine, like they can have them from all over the ring, I guess.
So technically, the first thing you do is you create the tokens and distribute them randomly over the ring. And then you assign the tokens to the machines. And when you assign the tokens to the machines, maybe you can be careful to not assign two neighbor tokens to the same machine, right? In order to avoid that, that the data is concentrated, right? But that you do when you assign to the machines. Does it make sense?
Thank you.
Yeah. All right. So the CAP theorem, I told you that in the beautiful world of big data, when there is a network partition, either you crash or you choose consistency or you choose availability. A very interesting use case is when you choose availability at the cost of consistency. This is exactly what we are doing right here. And what happens when you do that is that when you have an old system like that is always available, consistent, no network partitions, it would just crash if one happens. Then you basically have a linear timeline, right? Because everybody agrees at all points in time what the data is. So if you modify the data, then your new version of the data will be later on the timeline, right? You can even create a versioning system that keeps track of all the versions. So you have a linear timeline. But the thing is, when you have a network partition and you choose to remain consistent, you're going to have half of the network that is going to be on some version of the data, and other half of the network that is going to be on another version of the data, because then they will start modifying the data each on their side and they will no longer agree, right? And then something very weird happened because that actually throws you into space-time, right? Who would have guessed that? And in fact, in order to solve that problem, we just no longer have a linear timeline, but we have a DAG, a directed acyclic graph. Who knows Git? It's just like the Git branches that forms a DAG, right? When you have all these commits. So we do the same thing here, but it actually is a feature of space-time because that corresponds to the case that you start having space-like separation, like with Earth and Mars and so on. But let me show you what it means. So it means that we cannot use a clock like it's 1 p.m., it's 2 p.m., like we cannot have a linear clock. But we are going to be using what's called the vector clock. The vector clock was actually invented here at ETH, if I'm correct, by Friedman Mattern, who was a professor in the Department of Computer Science. And that actually made its way into plenty of products, including Amazon Dynamo. So here is how they work. You basically have a clock that corresponds to the node that handles the first request. So let's say it's node A. So you add the time for node A, you set it to 1. That's the first version. Then maybe you update it again on the same node. So you're going to say, okay, node A, that's version 2, right? So you increment for node A. And when you have a network partition, you might have on one side of the network, then some other node is going to take care of it, node B, one half of the network. And then it's going to increment for a new version of the data, its clock to 1, knowing that A was at 2, B is at 1, right? So you just increment the clock of B. It's called a vector clock because instead of having a single number, you have as many numbers as there are machines in the network, right? All the machines that don't appear here are at 0, right? You don't put the zeros. But the machines that did see the data once, they have a clock that they increment every time. So this is one half of the network that this has this clock. And the other half of the network, that's another node on the other half of the network, would be A also, but I just put B and C for more interesting case. So C would create a new version that would be a yellow square. And for the other half, it's a red triangle. And that's with the vector clock to C1, right? So it's a different vector clock. And then you are no longer consistent. Why? Because one part of the network sees this, the other part of the network sees that. This is why you drop the C in CAP, right? You are PA, right? Partition tolerant and available, but now you're no longer consistent. And what happens in these cases is that at some point, the network partition is solved and the whole network connects again, but then you have the problem of this disagreement on the data. Then you need to unify it. So the user is going to provide a new value that is going to take over on the two sides of the network. You basically reconciliate or you solve the conflicts. And what happens is that, imagine it's node A that does that. You merge these two clocks, A2, B1, C1, right? And you increment whichever node takes care of it, 3, 1, 1. What's actually happening here is that we have a partial order. This is the question I asked last week on Wednesday. A partial order corresponding to a DAG. It means that if you take two clocks, two vectors like this, either you can compare them and say this is greater than this is greater than this is greater than this is greater than this, or you cannot compare them. If you take these two, you cannot say that one is greater than the other. This is how you detect a conflict. When you solve the conflict, you create a new clock, a new vector that is both bigger than this one and bigger than this one. And now you have basically a maximum value. So this is called the maximal element. At that point, you have two maximal elements. But when you actually have a value that's bigger than everything else, then you have a maximum, right? This actually is larger than anything else. So if the system is functioning normally, there is no network partition, then you will have like this a maximum, like some sort of unique value that is greater than everything else. But if you have a network partition, temporarily you're going to have competing vector clocks that are both maximal elements, but there's no unique maximum. For whom does that make sense? Right? So network partition, and now it's solved. This vector clock is actually, is there a question?
So how do we do the conflict solving here?
It's the user. So I will show you an animation right now. It's the user that decides. You basically present these two values to the user, and you say now, please solve that for me. And the user of the system is going to answer with a blue pentagon saying, this is what I want to have as the new value. And then Dynamo is going to create that new vector clock that makes sure that this takes over, right? It's like Git, right? When you have a conflict with a Git repository, it's up to you to solve the conflicts and then commit it to the repo. It has to be done manually, but it's also not mandatory. You know, you can also live like this. It's fine. You have concurrent version, but the next time you try to update a value, then you have to handle the conflicts, right? That's the idea. All right. Okay. Now, this vector clock, you remember that I told you it's get, put, delete, the API, just like in REST. But I told you get and put actually have additional parameters. Get has what's called the context, and put takes a context. The context is actually a vector clock. Now you know what it is. And I'm going to show you an animation because there's nothing better than actually seeing it in action. So I'm going to take as an example, of course, it's very few nodes here for my slides. I wasn't going to draw 1,000 of them. Imagine we have a duplication factor of 3. So we have 3 machines that are responsible for it. I'm not using tokens, but it's the same idea with tokens, right? For simplicity, I'm just using 1 token per machine in that case. All right. So here you go. You have the system, and I'm focusing on 3 machines. So you have an incoming request that says, please put associated with key 1. I do everything with key 1. This is some key. Associated with the value A. A is some value like my rectangles and triangles that I had earlier, right? So let's put A associated with key 1. What happens is that the system you connect, there's a load balancer, and then it redirects you automatically, thanks to this table at some point, to a machine that is responsible for key 1, turns out to be N1 for that range of keys based on the hash of key 1. And then N1 handles it, creates a new context, vector clock is incremented by 1, and then it's storing the value A with the vector clock N1, 1. Key 1 is also here, but again, everything is key 1 in my example, so that's why I don't put it here. And then it propagates, right? Because 2 more nodes have also the responsibility of storing it because of the duplication that I told you about. So we replicate the same thing over the 3 nodes. It's possible because there's no network partition, right? So you can communicate with everybody here. Then if you get the key, you gather all the versions. You notice that they're all the same, so there's no problem in here, and you return this unique value together with its vector clock, right? And that's it. So you return that. And that's the context that you get from the get function. It tells you not only the value, but also the context. Then the user, or some user, maybe the same one or the one who did the get request, now wants to modify the value and put B instead. So it wants to put value B, and it has to resupply the context that it got from here, right? So it resays, okay, that was the context I had. Please now put value B in place. Now, N1 is still handling it because it's available, so it's going to increase the clock by 1. So now it's N12, so you store B with N12, and then you replicate, right? You don't have to delete the old version immediately, right? Since it's old version, then you know the version, then you can keep the older versions as well, right? It doesn't hurt. You can still clean up and prune a bit later, right? Then you try to get key 1. You gather everything. So you do have two values, conflicting values. However, if you look at the vector clocks, you can see that one is larger than the other. They do compare, right? And you see that N12 is larger than N11, according to my partial relation. So I'm returning just this one, which is the maximum that I have among my vector clocks. So I return B with the context N12. Then somebody else wants to add a new key, to add a new value with that key. So C now, again, N1, so you create a new context, +1, except that now, like in a Hollywood movie, there's a catastrophe and the network actually partitions. The cable between N1 and N2 is broken. So you see what's happening here. This value is blocked here, but doesn't propagate to the rest of the network because there is this network partition. But it's not a problem because we have a partition tolerant system. And it's a partition tolerant system that is AP, so it will continue to be available and it will continue to work, so you can continue to use it. Imagine that somebody connects from the lower part and wants the value for key 1. That's okay, it's going to work. You just pick the second node in the preference list, that's N2, and it returns the value B with N1, N2. That's okay, it's not the latest one, but that's what it means to not be consistent, right? You just don't return the values that would actually be the latest one because N1 is disconnected. So you return B, N1, 2. So imagine that now, whoever got B as the latest value wants to put D instead. So you create a new vector clock in that lower part of the network. It's N2 that takes care of it. So N1 remains associated with 2, but N2, this node here, is increasing its clock by 1. So I have N2, 1, and you're storing D like this, and at some point you will propagate. But now it turns out that the cable works again, so now it's all connected all over again. So what can you do? You propagate things again, right? So imagine that I try now to get key 1, even I didn't even have time to propagate. So let me get key 1. So now I gather everything. I try to gather all the versions that I can find in there. And I'm going to have these 4 different versions. I want the maximal elements, right? So I'm going to return which ones? 2 of these values. Which ones? C and D, exactly. Because A and B are not maximal elements. C is larger than A and B. And D is also larger than A and B. So A and B are not returned, but C and D are, you see, the maximal elements. These are the nodes that don't have any outgoing edge in my directed acyclic graph, DAG. And so this is what I'm going to return. They're not comparable. No one wins, so I'm returning the 2 of them, right? So that's it. I'm returning 2 values, C and D, with the vector clock N13, N21. And now, and this answers your question that you asked earlier, it's the user's job to say what instead of C and D you want to put, right? So the user can decide on a new value. So maybe they do. So now the user is thinking, okay, what am I going to put as a new value? In the background, the nodes are going to synchronize again, right? So you have, again, all the data can now be spread over the machines again. Maybe we can also do some cleanup while the user is thinking. So here A and B can actually be we can get rid of them because they are not maximal elements. Let me only keep C and D, right? That I can do periodically. Now there's an incoming request. Finally, the user made up their minds. So now we have E as the new value together with the old context. So notice that the context that the user was given here was taken as merging the 2, right? N13, N12, N21. So the merge of the two is N13, N21. That's just the merging, taking the max for all nodes. So now we take, that's the context. Now we take that context. And since it's N1 that's handling the request, because it's back online, so we increase the N1 counter, becomes 4. And now we have this new version E that I add everywhere. But now it's great because we again have a maximum, right? Who is with me on this? Right? Now we increment it and we again have a vector clock that is larger than anything else, right? So this is it. Now we have an absolute maximum and it means that the conflict is solved. Okay? So this is how you handle it. And there is again a very beautiful link between classical physics, like Newtonian physics, with absolute time that would correspond to a system that is always consistent. You just have an absolute elapse of time, a linear view, and an absolute complete order, right? It's a full order that's complete order. I can't remember the adjective now. Okay, the one that basically is a straight line. You have a DAG that is in a straight line. But if you have conflicts and you want to not be consistent in case of network partitions, then time becomes a DAG like this, right? And these kind of graphs you see everywhere in special relativity or even general relativity when you have a structure of space-time with that kind of dependency graphs. But I think as computer scientists, you've seen these graphs already plenty of times, right? So who has seen a graph like that, right? Almost all of you. It's classical theoretical computer science. All right, so this is it. Vector clocks correspond to partial orders, correspond to DAGs. I had a few last words very quickly about Amazon, Azure, and so on. So the idea is that even though the cloud providers are very similar in the things they offer on the high level, so Google Clouds, Microsoft Azure, and Amazon AWS. On Amazon, there is a tendency to have plenty of small services. You have a service like S3 for storing objects. You have a service for relational databases. You have a service to rent machines. You have a service for your domain. You have a service for the DNS zones and so on and so on. So you have maybe hundreds or more services on Amazon, and you can just help yourself through the console to use all of these services, right? Azure has a bit of a different approach and has a few products that do more things, right? So it's less distributed across plenty of services that do only one thing, but you have, for example, database management systems like Cosmos DB that handle different things. So the key value paradigm that we saw, but together with graphs, tables, trees. So it's ongoing research to try to unify the data shapes, and so you do have work that goes in that direction. Okay, and this is where the part on cloud storage is ending, right? So we saw S3, which is object storage for objects sized up to 5 terabytes worldwide, a service that you just pay for and that is hosted by Amazon. And you have, on the other hand, key value stores like DynamoDB that handle smaller objects up to 400 kilobytes, right? But they are faster. They have a much lower latency as a result. And you know that this is done with the CORD protocol and that I've described here. Do we have any questions? On Zoom? No questions on Zoom? I also wait a bit for questions, because when you ask a question, then as a student, I knew like the moment I want to ask the question, the professor already continued to something else. So no question, right? Okay. So if that's the case, then I'm going to move on to the next part. I'm going to stop the recording.